So I'm going to make up a problem. Once again, related to physics. We are going to do some non-physics examples hopefully today, and then definitely more next Monday. But again, it's sort of easiest to think about initially in terms of physics. This is going to be yet another motion example. And this motion example is not one directional. It's going to go back and forth. It's not going to be free fall. So I'm not pretending it's an object falling under the influence of gravity now. I'm going to pretend I know the formula for not the distance traveled, but the position of an object. Maybe you could pretend you're in a car and you're driving the car back and forth, or well, maybe that's not such a great example because you have to turn around real quick, but maybe it's okay. Maybe it's like a fly flying back and forth in a straight line. Now, flies don't really fly in straight lines, but you can pretend. And S is, or let's make it a Y. Y is going to be the position of an object along a line. And let's go ahead and use standard units in meters, say. And this is going to be a function of time. T is time. And the usual units would be seconds. But these can be different things. Y could be in miles and T could be in hours. The units you use are arbitrary, but they do affect the formula. And it might seem artificial, but it's certainly simplest to do it at first, to come up with, say, a simple formula for the position. I'm going to come up with one that's a cubic, and I'm purposely making it going to have roots at 0, 1, and 3. So to make a cubic that has roots at 0, 1, and 3, I need some constant. I'm going to pick the constant to be 1 times t minus 1 times t minus 3. So that's going to be a cubic polynomial with intercepts at t equals 0, t equals 1, and t equals 3. It's in factored form. This form, it's easy to see the intercepts, but it's not so easy to see what the derivative would be. You want to expand it out, multiply it out. So I'll multiply the t minus 1 times the t minus 3 first by foiling. FOIL, first times first is t times t is t squared. Outside times outside is t times negative 3 is negative 3t. Inside times inside is negative 1 times t is negative t. Negative 3t minus t is negative 4t. And then last times last is negative 1 times negative 3 is positive 3. And then multiply the t through to get t cubed minus 4t squared plus 3t. So yeah, again, that's kind of artificial. You know, when would you ever have a position function that's a cubic like this? Probably practically never. But for the sake of keeping things simple, we pretend we've got formulas. Turns out with more arbitrary kinds of situations, you can often find formulas that approximate the position that are often polynomials, for example. So it's not as artificial as it might seem at first. All right, we're going to find the derivative of this. Written in our two ways, f prime of t. This emphasizes that the derivative is a function when you use this notation. Of course, we can plug in numbers for t as well. I could do this with a limit. I'm not going to do that today because we have other things that we need to do, and it's going to take too much time if I do that. So today I'm going to use some rules for derivatives that if you've taken calculus before, you probably remember the best out of the course, the thing you remember the most. We're going to use those rules here. And for those for whom this is new, I'm teaching you these rules now for the first time. And yes, they might be the thing you remember most a year or two from now. I'll use the Leibniz notation as well. dy dt. Both of those stand for the derivative. This emphasizes that the derivative is a function of time. Different t's will give you different derivative values, different slopes of different tangent lines on the graph, right? The graph is going to have infinitely many tangent lines because I can find the tangent line at any point. And those tangent lines will have infinitely many different slopes. And I can find the slopes by plugging t into whatever formula that I get. This notation emphasizes the derivative as a rate of change, because this kind of looks like a fraction that represents like a change in position divided by a change in time. In other words, a velocity. That's what this notation is supposed to remind you of. And it doesn't hurt, and sometimes it's even helpful to pretend it's a fraction. One more notation I'm going to use here is I'm going to write d dt by itself. And then in parentheses, I'm going to put the function that I'm differentiating, this thing here, t cubed minus 4t squared plus 3t. That function is y. So I've effectively replaced the y by that function. When I use this notation for the derivative, I'm emphasizing yet another aspect of the derivative. I can think of this d dt as being what's called an operator that operates on something, not like a surgery or something, but it does something to something. It differentiates a function, in this case, a function of t with respect to t. Here's your function of t. This says differentiate it, d, with respect to t, dt. It's a little weird, but that's the way it goes. Here's your first key abstract property of derivatives that we will use constantly for the rest of the course. This is the derivative of what's called a linear combination. This is a linear combination of some functions of t cubed, t squared, and t, say. What in the world is a linear combination? It's when you've got a bunch of functions, in this case, and you are multiplying them by constants and adding them and or subtracting them. So I got t cubed, that means the same thing as 1 times t cubed, minus 4 times t squared, the constant 4, plus 3 times t, the constant is 3. That's called a linear combination. You can have linear combinations of other things in math and science as well, like vectors, for example. If you know about vectors, you can multiply vectors by numbers, often called scalars, and you can add them and you can subtract them. You can form linear combinations of vectors. A key property of derivatives is that the derivative of such a linear combination is the corresponding linear combination of the derivatives. What in the world does that mean? Well, again, the t cubed has a 1 in front. It means the derivative of this is, well, the first coefficient, the first constant, 1, times the derivative of the first term, t cubed, minus 4 times the derivative of t squared, the 4 comes out in front, plus 3 times the derivative of t. Write it exactly like I'm writing. Although, yeah, you don't have to actually put the dots in there for the times, but I did. That is a fundamental property of derivatives. I always call this the linearity property. That's my name for it. It's a name other people use as well, but maybe not everybody. The linearity property of derivatives. Some people might call it a superposition property. Just like in physics, when you have a bunch of different waves and you're combining them, adding them, so to speak, it's a superposition. It's kind of analogous to that here. We're adding these terms to get a new term, a superposition of them, and then we're taking a derivative of that, and you can do it to each piece. Just like with waves, you can kind of analyze each piece separately and then add the results together. But I will usually call it linearity. And that's a linear combination. The presence of the word linear in both spots is not an accident. Do you always have to show this work? Not always, but do it at least in section 2.3 problems if you encounter it from now on, and possibly in section 2.4 and 2.5. But then once we get to chapter 3, you will not have to show those steps all the time. You will be able to ultimately jump to the answer, but I want to emphasize the property because the property is key for more than just getting the right answer. It's also a key property for higher math, where the property is used more in the abstract. The class I'm thinking of is called differential equations. This linearity property is used all the time in differential equations. And also linear algebra, and if you need to take differential equations in linear algebra, you might be taking that with me next fall, at least if you take Calc 2 during the summer, or maybe the next year, like if you're an engineering major. Property is very, very important. So it's worth emphasizing. Now we use, to find this, this, and this, the property that people remember the most. It's called the power rule. Again, in your book. I pointed this out the other day. Find it on page 95, section 2.3. I'll just show it to you here. Oops. Sorry. If f of x is x to the n, then f prime of x is n times to the x to the n minus 1, no matter what n is. N can actually even be a fraction, or even an irrational number, and this still works. Though it might be confusing, what would it mean to raise x to the pi power, for example? What in the world would that mean? Well, we won't get into that, but it's still true. In effect, you bring down the power in front as a multiplier, n times, and you subtract 1 from the exponent. You take that exponent n and you subtract 1 from it to get a new exponent of n minus 1. I'm going to use that property here, except my variable is t instead of x. I'm going to put the constants there just for extra emphasis again. That's like an x cubed, except it's a t cubed. Well, I'm differentiating with respect to t. That's what this notation tells me. T is the variable. I use the same rule with t as the variable. Take that power, that 3, bring it down in front, multiply it by t to the 3 minus 1 power, subtract 1 from it, which you can just go ahead and write as 2 right away. Then do minus 4 times the derivative with respect to t of t squared. Same rule applies. Now n is 2. Here n was 3. Here n is 2. Bring that 2 down in front. Multiply times t to the 2 minus 1 power. 2 minus 1 is 1. I will write a 1, but of course you wouldn't have to because t to the first equals t. You do have to write a t squared there. With this one, the n is 1. This is t to the first. So bring that 1 down in front, subtract 1 from the exponent, you got t to the 0. Is t to the 0 1? Yeah, it's a trick question, actually. It is 1 if t is not 0. Technically, 0 to the 0 power is undefined. But we don't worry about that little technicality here. We treat this as a 1, and therefore this entire thing is a 3. It works. We don't worry about the technicality that technically 0 to the 0 power is undefined. This does give the right answer. Simplify a little bit. Your final answer is 3t squared minus 8t plus 3. There's the derivative. And that would be the velocity. Let me go back to the beginning and mark this as a v for velocity. And it would have units of meters per second. And if the units of distance were miles and the units of time was hours, its units would be miles per hour. Right? It's units of distance per unit of time. And it is a function. I can use this to find the slope of the tangent line to the original graph at any time I want. What is f prime of 1? Just plug it in. 3 times 1 squared minus 8 times 1 plus 3 gives you -2 meters per second. Yes, it is -2. What does that mean? It means your velocity is negative, which means you're traveling in the negative direction, whichever direction is negative. How do you know what direction is negative? You decide. You get to decide which direction is positive and which direction is negative. But once you make a decision, that does affect your formula. If you use the opposite direction than what I decided to say here initially, then your position would actually be the opposite of this function if you switch the directions of which direction is positive and which direction is negative. If I want to find the derivative at 2, plug in 2. 3 times 2 squared minus 8 times 2 plus 3 is 12 minus 16 is -4 plus 3 is -1. Let's do one more. What's f prime of 3? 3 times 3 squared minus 8 times 3 plus 3. 27 minus 24 is +3 plus 3 is +6 meters per second. At time 3, your instantaneous velocity is positive, so now you're traveling in the positive direction. Are there any places where the velocity is 0? Is that ever 0? Well, it changes from negative to positive, so there must be a place where it's 0, right? Actually, that's something related to continuity in chapter 1 that you should have read about, called the intermediate value theorem. I haven't talked about it in class, though we will. It's quadratic's continuous. If it's negative somewhere and positive somewhere else, it's got to cross the horizontal axis somewhere. I'm not drawing the graph yet. So, yeah, there's got to be a spot where it equals 0. How do you find it? Try factoring or use the quadratic formula. I think I probably need the quadratic formula because probably the velocity is 0 at some irrational value. That's most likely what's the case. If I set v equal to 0, f prime of t equal to 0, and solve for t, that means 3t squared minus 8t plus 3 equals 0. So use the quadratic formula, which you should memorize. You really should. Take the negative of that coefficient, which is 8, plus or minus -8 squared is 64, minus 4 times 3 times 3, 4 times a times c. All over 2 times a is all over 2 times 3. 4 times 3 times 3 is what, 36. 64 minus 36 is 28. Do a little simplification. 8 over 6 is 4/3. We're going to get 4/3 plus or minus 1/6 square root of 28, it looks like. Yeah, 28 is not a perfect square. This is going to be an irrational number. This can be simplified a little bit. Do you have to simplify it? No, but it's not a bad idea to know how. 28 is 4 times 7, so this is the square root of 4 times the square root of 7, which is 2 times the square root of 7. So in simplest form, you could write this as 4 plus or minus, the 2 cancels with the 3 to give square root of, with the 6 to give a 3. Square root of 7 over 3. You can write this as one fraction as well. Those are the 2 spots where the velocity is 0. Square root of 7 is, well, between 2 and 3. So both of these numbers are positive. There's 2 positive values where this equals 0. Let's approximate them. 4 plus square root of 7 divided by 3. Hopefully I haven't made a mistake. Let me know if you think I make a mistake here. Again, I do make plenty of mistakes, so there's one of them. That's the bigger one because that's the one with the plus sign. And then 4 minus square root of 7 divided by 3 is about 0.451. At those moments of time, your velocity is 0. What does that mean? What does it mean for the velocity to be 0 for this motion and positive and negative elsewhere? Physically, what does that mean as far as the motion goes? Not moving at that moment in time, but what does that really mean practically speaking? Yeah, for an instant, you change direction. It's like the fly, which can change directions quickly, is essentially flying in one direction and slowing down ever so slightly to be able to turn around and come back the other direction at some moment in time. You might wonder, really, is there really a moment in time where it's not moving? That's maybe more of a philosophical question or something. I'm not sure. But as far as the mathematical modeling goes, effectively, there is a moment in time where the velocity is zero, where the fly turns around. Let's look at the graphs of both the position function and the velocity function and see if they make sense. In fact, let's go ahead and use Mathematica now. And so if you've got Mathematica open, that's good. If you don't have it open, you should get it open. I will share this file on Moodle, but it wouldn't be a bad idea for you to do this. In fact, question? Okay. I was going to have you do that, but you tell you what. Okay. I don't know. Go. What were you going to say? Yeah. Okay. In some form, I'll have you turn this in. Maybe as a PDF file, just because that'll make it easier to look at on Moodle. You can save mathematical files as PDFs. You can do a save as, and you can convert it to a PDF. Okay, and that would be a nicer way to upload it onto Moodle. Okay, so let's enter this function. So go ahead and do this with me. You should see a horizontal line there. You're not going to have this typing here, of course. When you see a horizontal line, that tells you Mathematica is ready for input. So let's type the function in here. Remember that you need, well, first of all, a function name. I'm calling it f. Then you use square brackets, not parentheses. Parentheses are reserved for when you're multiplying things, not function inputs. Square brackets are used for function inputs. Then put a T, then put an underscore. Remember, I've emphasized you need to put an underscore when you're first defining a function. After you've defined the function, you don't need the underscore anymore. Colon equals, the colon is actually optional, but I like doing it. T cubed, you can type like that, minus 4t squared plus 3t. There's the original function. To enter this, make sure your cursor is somewhere in this cell. Notice this thing, by the way, over here on the right, that indicates we are in a cell of input. It doesn't matter where the cursor is. Enter it by doing shift return. Hey, nothing happened. Well, actually something did happen. You just don't see any output. It's stored this formula in its memory. And now if I type f of t without an underscore and do a shift return, it spits back the formula at me. Yes, it is stored in memory now. By default, it goes low degree to high degree, even though when we do it by hand, we usually type it high degree to low degree. It is stored there. If I type g of t, well, I've got something in memory. Okay, let's clear g. I can clear f, by the way. I can do this, clear f, and then if I type f of t, then nothing. So I just type clear f to clear out the function f from Mathematica's memory. By the way, yeah, I've had Mathematica open for a while. That's why you see an in 586 here when maybe you're only seeing like an in 2 or in 3 on yours. Because I've had Mathematica open for a while here without closing it. When you close it, it goes back to in 1 and in 2. Those stand for input 1, input 2, out 1, out 2. That stands for output 1, output 2, etc. Hey, but if I've cleared it, how do I work with it? Well, just go back and re-enter it. Now it's entered again. Let me get rid of the clear. You can cut things out by highlighting the cells over here and just doing a standard Command X or something to cut it out. Or you can go up to the file and cut as well. Yeah. Command cut would be Command X in the edit menu. So it's stored. What's its derivative? Hey, here's a quick way to find the derivative. Just type f prime of t and do a shift return. There it is. We got the right answer. I'm not going to require you to do this, but I would encourage you after class to try to derive f prime of t from the limit formula. And guess what? It can actually be done in Mathematica as well. I can type limit with a capital L. Then I can get this palette to get a fraction. To get the palette to show up here, the writing assistant, you can go up to the palettes menu and go to writing assistant, and then this kind of thing will show up over here. And when you go to the typesetting part of that down here, open this up, you'll see various buttons, like there's one that's a fraction. I made that fraction by clicking on that button. Not that you have to make fractions that way, you can just do a slash. But I kind of like doing that. It's a limit of f of t plus h minus f of t, all divided by h. Is that good enough? Will that calculate the limit? Well, I see a little red thing there. It didn't do anything. Why not? Well, because I haven't said what's happening. I'm letting h go to 0. I have to let Mathematica to know what to do with h. So type a comma, then type h arrow with a minus sign and a greater than sign. Makes an arrow, and when I type a 0, it magically morphs into a better looking arrow, 0. And now, lo and behold, I get the exact same answer. Yay, math is consistent. That linearity property really works. We got the right answer. That's the way to compute the limit in Mathematica. That computes the derivative in this case. Capital letters for built-in commands like limit are absolutely necessary. You need a capital L there. If I did a lowercase l, it would not work. Built-in functions in Mathematica come with capital letters in certain spots, certainly at the very beginning of the word. Let's plot the function and its derivative on the same set of axes. That's always a good thing to do. And in fact, you're going to have some exercises due Monday where you're given just graphs and you want to plot the derivative. Graphs like these things in the book. Like these pictures. Those are graphs of arbitrary f's without formulas. And you're supposed to draw the graph of the derivative from those things. How in the world would you do that if you don't have a formula? Well, you're trying to estimate slopes. That's how. So if we looked at, for example, this one right here, what you'd want to do is maybe get a pencil and lightly draw some tangent lines and estimate their slopes. And once you got the slopes of those tangent lines, that gives you values of the derivative, because that's what the derivative tells you, is slopes of tangent lines. And once you get the values of the derivative, you can plot the derivative. Let's illustrate it here with our example. I mean, Mathematica is going to make the plot for us, but we can try to see if the plot makes sense. So I'm going to plot both f of t and f prime of t. Notice the capital P. Notice the square brackets. Notice the red arrow. The red little caret symbol is telling you you need more input. I'd like to plot both functions at the same time. If I was just after one function, I'd type the one function in like that. But I'm after both. If I want to plot both functions at the same time, I need to put them inside curly braces like this with a comma. Mathematica is very sensitive to doing the correct syntax, at least when you are in the standard mode. There are non-standard modes where it guesses what you want to do, just like Wolfram Alpha, if you've ever used Wolfram Alpha. In fact, Mathematica is made by Wolfram, the same people who do Wolfram Alpha. So there are ways to have it guess what you want. But if you want maximum flexibility to force it to do what you want, then you want to learn the right syntax. Commas are absolutely necessary where you see them. Square brackets where you see them. Curly braces where you see them. All necessary. Still see a little red caret here. I need more input. What kind of input? Well, the range of values for t would be good. And since our intercepts are at 0, 1, and 3, and we're going to maybe imagine starting time at 0, let's let t go from 0 to 4, say. Notice I'm putting that inside curly braces as well. That's, again, called a list. T first, that's the independent variable, comma, 0, that's the T min of your window, comma 4, that's the T max of your window. If I don't put that plot range in here, Mathematica will pick a plot range for me. It looks like if you look at the vertical direction here, about -5 to 20. Is that the best plot range to pick them? That seems reasonable. Notice the scales on the axes are different. 1 unit on the horizontal axis is this far, but 1 unit on the vertical axis is this far. That means it does make it a little bit, well, deceiving as far as slopes go. For example, this slope of the blue graph here looks not very steep, but it's steeper than it looks. Because if I made the scales the same, you'd see it look steeper. Let me actually modify this to not have such a wide scale in the vertical direction. Well, for one thing, by going maybe instead of to 4 to maybe 3.5. Well, let's do 3.3. What did I do there? I just copied and pasted. That's one big benefit of Mathematica. It's easy to copy and paste stuff. So I went up to this cell. I did a Command C for copy, and then I went down here and I did a Command V for paste. But of course, you can use the edit menu as well to do your copy and paste. But make sure your cursor is on the cell you want to copy and paste. And yeah, I went down here until I saw a horizontal line, and then I knew I was ready to paste. Whenever you see a horizontal line, that's what it means it's ready for input. So I picked a smaller T window here so I can sort of zoom in a little bit like this. The scales are still not the same. Let me modify this to try to make the scales the same. And I'm also going to change the Y direction to being smaller than what we see here. I'm going to put a comma in here and type plot range with a capital P and a capital R. Arrow is a minus sign and greater than sign. And inside a list, I'm going to put the Y min and the Y max, but I don't need to put the letter Y itself. I'm going to go negative, let's go -5 to -3 to +5, say. And it changed the plot range to being -3 to +5. The blue graph is f of t. The goldish colored graph is f prime, right? The blue is a cubic. The gold one is a quadratic. The position was a cubic. The velocity was a quadratic. Remember that? That's what we found for these formulas. Position was a cubic. Velocity is a quadratic. And we can see that from the graphs. It's a little still hard to estimate slopes in here. I'm going to do a few other things to try to estimate slopes better. And you can do exactly what I'm doing. You can enter something and then put new code within the same line and re-enter it. So I'm putting another comma now. And if I want the scales the same, what I need to use is a command called aspect ratio, capital A, capital R, arrow. I always forget if is it a 1 or is it an automatic? They might both work. Let's try 1. That looked like it worked. That actually is still not quite right. Maybe it's automatic. That's better. That's actually what we want. Let me make this a bit smaller so you can see it better. And maybe I should make the plot range even smaller. Let's just go -3 to +3. We won't be able to see much of the velocity graph, but this is good enough. I'm trying to make the scales the same, and I just did that with this automatic there, so that I can estimate derivatives better visually. That's my purpose. But it would also be nice, like the book's problems, to have some grid lines in there, like it's graph paper. Well, that can be done as well. Put another comma, grid lines, capital G, capital L, arrow. I could try automatic and see if it's good enough. That's actually not what I want. but it's okay. It's okay. We can use this. Be careful. Notice it's putting more grid lines in the vertical grid lines every half unit and horizontal grid lines every unit. I was hoping it would do every unit for vertical lines as well, but it's not a real big deal. So these are not squares. They are literal rectangles that are not squares. The base is a half and the height is 1 for each of these. But now I can try to estimate slopes. Look at the blue graph. That's the position. What's the initial slope? Imagine drawing a tangent line there. In the book, you can literally draw on your book if you want. If you want to draw lightly. If you think you might want to sell your book, maybe you shouldn't, but draw a little mini tangent line and then maybe extend the tangent line. The tangent line, what's its slope? It does appear to be somewhere between, say, 2 and 3. The value of the derivative at 0 is actually 3. So the tangent line here is actually 3. It's steeper than I was initially showing. It's about like this. So the value of the derivative is 3. That's why the second coordinate on this gold graph is 3 at t equals 0. Draw another tangent line maybe here at t equals 0.25. What's its slope? Well, follow it forward. What's its rise over its run? Pretty close to 1, it seems. For every 1 unit you increase here, the vertical direction of the slope, you increase by about 1 unit as well. If you can't see that and think about it as I'm talking about it, just at least try to get the idea and imagine, yes, I definitely can do this in my book, maybe with a ruler to help me draw tangent lines. Estimate a slope of 1. Hey, guess what? The value of the derivative is close to 1 there. And in fact, it's exactly 1 right there. So the slope of the tangent line is exactly 1 right about here. The slope of the tangent is 0 at one spot, right about here. There's a horizontal tangent. Hey, that's where the derivative is 0. And look, the derivative is 0, that gold graph at 0 between 0.4 and 0.5. Between 0.4 and 0.5. 0.451. That's an example of a moment in time when the bug changes direction. At that moment in time, the instantaneous velocity is 0. The position graph has a horizontal tangent line, and the derivative graph has a horizontal intercept. F prime of t is 0 there. It's really key stuff. Then you continue going. Now the slope of the blue graph becomes negative. So that means the derivative has to have a negative value. Yeah, the gold graph is negative. It's below the horizontal axis. Horizontal axis is right here. And it's most negative. The blue graph is steepest, and the negative slope may be right about here where the derivative has a minimum value. And what is the slope right about here? Well, again, you could draw a little tangent line. And if you do it real well, evidently you should get a slope maybe close to negative 2.3 or so, because I'm looking at the derivative and I'm seeing the second coordinate at this point is close to negative 2.3 or so. Is that really the lowest point? I don't know. I'm estimating. I'm eyeballing it. I could solve for where f prime of t equals 0 and, excuse me, f double prime of t, the derivative of the derivative, which I do want to introduce today. It's actually 0 at 4/3. The derivative of the derivative, called the second derivative of the original function, is 0 when t is 4/3, which is 1.3 repeating. 1.3 repeating is right about there. That is where the graph of the velocity is lowest, most negative, which doesn't mean that the bug is traveling slowly, right? Because it's a negative velocity that's just most negative. It's actually traveling fairly fast then, but in the negative direction. You really, really need to think carefully about all these physical connections to fully understand this. At this moment in time, the bug has not stopped because this graph, its slope is not 0. It's a negative slope. The bug is traveling in the negative direction. And in fact, it's going fastest in the negative direction at that moment in time because the derivative, the velocity, is most negative there, furthest away from 0 in the negative direction. And what is the velocity there? F prime of 4/3, negative 7/3, about negative 2.3, just like I guessed. Now the bug's still traveling in the negative direction here, but it's slowing down because the slope is getting closer to 0 here. The velocity graph is still negative, but getting closer to 0. At this moment in time, between 2.2 and 2.3, the velocity is 0 again. The bug turns around again at that moment in time, when this graph has a horizontal tangent and this graph is 0. Bug turns around, is now traveling in the positive direction, has a positive velocity. Its position is still negative here. Y is still negative, but it's traveling toward the positive values of y. Its velocity is positive. Its derivative is positive once t is past about 2.21. It's a back and forth motion here. In the positive direction, turn around, go in the negative direction a bit further, turn around again, go in the positive direction. You need to be able to imagine that, maybe along the y-axis. Watch my cursor here. I'm going to try to mimic this motion. Imagine time elapsing at a constant rate. The bug goes up, then comes back, goes faster and faster, then slows down, then turns around again and goes back and continues to go faster and faster because this blue graph gets steeper and steeper. The gold graph gets higher and higher once t gets past 2.21 again. So important to be able to relate the formulas and the graphs to real life. Use your imagination. Imagination is very important in math, in having success at math. To really get what this is about, you got to have imagination and use your imagination in the right way. Can I clarify anything? Please let me know if I can clarify anything. Fundamental stuff here. And yeah, there is a second derivative. The second derivative is the derivative of the first derivative. Doing it on paper, and using correct notation, there's a concept of something called the second derivative. When y is position and t is time, the derivative of position with respect to time is called the velocity. And the second derivative is called the acceleration. The acceleration A, when f of t represents position, is the second derivative of the position, which could also be written, so we say f double prime of t there. You could also think of this as the derivative of the derivative. You could write f prime prime of t. That's really a definition of what the second derivative is. With the Leibniz notation, you could write this as, well, dv dt, in other words, the derivative of the velocity, or the second derivative of the position, which is written a little strangely, d squared, so to speak, y dt squared, so to speak, is the notation, the Leibniz notation for the second derivative. Now, am I literally squaring there? Not really. The d is not a number. I'm not squaring d. The dt is not a number. I'm not squaring dt. So why do it this way? Why put this 2 there and this 2 there? It's because you are applying the operator, the ddt, twice. That's why. You could think of this as ddt of v, but the v can be thought of as ddt of y, And you're not multiplying these operators, you're really composing them. Do d dt, then do it again. But if you pretended that you were multiplying them, then it would be like you are, well, let me go ahead and write it this way. It would be like you are squaring the d and squaring the dt. You could write it like that, though it's more traditional to write it like this. Weird, 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 but yes, it is the way it's done, and it's the way it's thought about. I'm telling you exactly how to think about it. d dt of v means find the derivative of v with respect to t. d dt of y means find the derivative of y with respect to t. I'm doing both things. First that derivative, then that one. It's like function composition. It's like f of g of x. Question?
Is that why it's like helpful to think about it as like meters over seconds?
No, the fact that we write units for acceleration as meters per second squared is more because we think of the units as meters per second. And then it really is more like you're multiplying units to get seconds squared. It's not a literal multiplication. It's just a convenient way to imagine it. It's still a convenient fiction, I guess you could call it that way. But this is not a multiplication. This is combining operations like function composition. But when you write that, it's kind of like you pretend you're multiplying them, even though you're not. And then, yeah, it's more common to put the y up in top. And for this example, what is this acceleration? Well, what was the velocity? It was this thing. I got to differentiate that to get the acceleration. Let's try it. Guess I'm out of room on this piece of paper. The acceleration is the derivative of the velocity, but the velocity we found to be 3t squared minus 8t plus 3. Hey, that's a linear combination. 3 times t squared minus 8 times t plus 3 times t to the 0, or 1 if you like. That's a linear combination. By linearity, there's our linearity again. That's 3 times the derivative of t squared minus 8 times the derivative of t plus 3 times the derivative of 1. This is a bit overkill here, but it's still worth emphasizing. Now use the power rule. Derivative of t squared, bring down the 2, subtract 1 from the exponent. Derivative of t, bring down the 1, subtract 1 from the exponent. Derivative of 1. Well, 1 is like a t to the 0 power. Again, not worrying about the fact that technically 0 to the 0 power is undefined. Bring down the 0 and subtract 1. Okay, I'm writing that, but you don't have to. You can just think of this as a 0. I mean, you could have thought of it that way originally because you were differentiating a constant. The derivative of any constant function is always 0 because constant functions have slopes that are always 0. Their graphs are horizontal lines. Doesn't matter what the constant is. Okay, I think that's the only time in my life I've ever written that. 0 times t to the negative 1 for differentiating 1. I'm serious. I don't think I've taught calculus like 30 times. I don't think I've ever written 0 times t to the negative 1 as the derivative of 1, except just right now. I did it just for fun. To kind of emphasize the power rule still works, even when the power is 0. But usually I just write a 0 there. I don't know, it just popped into my head and I thought of doing it that way. Simplify. 6t minus 8 plus 0 is just 6t minus 8. And yeah, that is what Mathematica got, but it wrote it as negative 8 plus 6t. Can you graph the acceleration too? Sure. Let's do it. Let's copy and paste. Copy and paste. and just put an F double prime in here, put a comma, then F double prime in T. The green graph is the acceleration. Notice acceleration can be positive or negative. It's more difficult to interpret it that way, though. You know, when you're accelerating, you feel it, right? You hit the gas in your car to try to go as fast as you can, accelerate as fast as you can. You're going to be pushed back into your seat. You slam on the brakes, you might hit the steering wheel. When acceleration is far from zero, positive or negative, you feel it. But thinking about whether it's positive or negative gets very confusing. If you're traveling along the freeway, constant speed, all of a sudden you see an accident coming at you really quick, you slam on the brakes. You are decelerating, you might say. But that means in the positive direction, you are slowing down. Your velocity is decreasing. That means your acceleration is technically negative. If you're speeding up in the positive direction, then your acceleration is positive. However, if you're traveling in the negative direction, maybe you're in reverse and you're going backwards along the freeway, please don't do that. If you hit the gas as you're going backwards, your acceleration is actually negative because you're accelerating, you're going faster in the negative direction. And if you hit the brakes as you're going backwards, then your acceleration is actually positive, even though you're slowing down. So it gets pretty confusing. You got to be careful to think about it. Does this make sense? That it's negative until t reaches 4/3 here, that the acceleration is negative. The bug travels in the forward direction at first, but is slowing down. Acceleration is definitely negative at first. It's still negative here, though, because now it's getting faster and faster in the negative direction. That's still a negative acceleration. After this point of time 4/3, it's traveling fast in the negative direction, but it's slowing down. So now the acceleration is actually positive. And then now it's speeding up in the positive direction, so the acceleration is still positive. Very important to be able to think like this. Takes practice. And it takes more than just listening to me this past 45 minutes or whatever it's been. You have to rethink about these things again and again to really get it solid in your mind. So that emphasizes the ideas of symbolic derivative calculation, notation, second derivatives, thinking about things graphically. You'll need to practice that in your homework. I'm also going to assign some problems where you think about the conceptual real-life meaning of derivatives in situations that are not necessarily about physics. So let's go through a couple examples like that. It's in section 2.4 that I'm thinking about. I am assigning, as you've noticed, problems from different sections. I'm trying to do in each given section, have assigned sort of the easier problems first and the harder problems later. I'm trying to approach this holistically and say, it's really good to think about these concepts in physics examples, for example, all at once to really tie things together. But then you read, of course, in a linear way, and these problems are in different sections. Go ahead and take a look at number 1. The cost C in dollars to produce G gallons of a chemical is a function. Using units, explain the meaning of the following statements in terms of the chemical. Use your imagination here, but also use your common sense. So it's a manufacturer producing a chemical. The more of the chemical they produce, the more it's going to cost. F is going to be an increasing function. And if it's differentiable, if the derivative exists, which is what differentiable means, that derivative will be positive in all likelihood. The slope of tangent lines will be positive. That's a good thing to think about. Now we want to think about these function statements. What do they mean? You got to think about the variables and what they mean and what are their units. So C equals f of g. C is a cost. It's in dollars. G is an amount of chemical. Amount in gallons. When I say f of 200 equals 1300, I'm saying that when G is 200, C is 1300. In other words, and since C is a cost, it costs $1,300 to make 200 gallons. This means it costs $1,300, include units, to make 200 gallons. That's what it means. What about the derivative statement? It's helpful to think about the derivative statement with the Leibniz notation as well. In general, if C equals f of g, that means dc dg equals f prime of g. And that's worth writing down because it emphasizes what the units for the derivative dc dg are. Units of C per unit of g. Dollars per gallon. This is in dollars per gallon. G itself is still in gallons. G itself is still the amount. But the derivative has units of the top variable per unit of the bottom. The D is just, it's there kind of acting like a delta. Small change in C divided by small change in G is a way to think of this intuitively. Not rigorously, but intuitively. If you pretend it's a fraction, its units would be dollars per gallon. It's what they call a marginal cost. What's the cost of producing one more gallon, approximately? That's what the derivative tells you, because of linear approximation. What does it equal? We're told f prime of 200, when you produce 200 gallons, f prime is 6. What does that tell you? It means when you are producing 200 gallons, the marginal cost, the rate of change of cost with respect to gallons produced, is $6 per gallon. When 200 gallons are being produced, let's go ahead and write it out with rate of change language. The rate of change of cost with respect to, you can abbreviate to WRT, with respect to gallons produced is $6 per gallon. That's also called a marginal cost. You don't have to write that down unless you want to. But what does that really tell you? So, if you produce one more gallon, your cost will go up by about $6. And it is an approximation. It's a linear approximation. And that means we can actually even write down what the cost is approximately. It was $1,300 when we produced 200 gallons. So when we produce 201 gallons, we should estimate the cost to be $1,306. So f of 201 is approximately f of 200 plus f prime of 200 times delta G. Delta G is 1. This is 1,300 plus 6 times 1 is $1,306. It is an approximation. The cost graph doesn't have to be straight. And you would think it might be in real life, but actually even in real life, it doesn't have to be straight. Oftentimes your cost graphs are kind of look like cubics, actually. They might look like that. That is what practically happens a lot of the time in real life. And if we pretend 200 is right there, and we pretend this is 1,300, the derivative being 6 means the slope of the tangent line there is 6. And in doing this approximation, we've approximated the change in the purple graph by a change in the red graph, just like we talked about with the physics examples. We're about out of time. I was hoping to do at least one more example from section 2.4. The examples all have a very similar feel to this one, except different situations. This one was about cost depending on gallons produced. This one is about the time of a chemical reaction depending on the amount of a catalyst present. Interesting. Time in minutes, catalyst in milliliters. So the derivative of this would be dt dA. It would have units of minutes per milliliter. For every extra milliliter of catalyst you add, how does that change how fast the reaction goes? It actually should be a negative derivative there, right? Add more catalyst, probably the reaction is going to go faster. dt dA should be negative. Is that the case? Yeah, here they're saying it's negative. Temperature is a function of time. Same thing there. Cost is a function of ice cream sold or something, or produced. There's lots of different situations here. Very important section. If you are looking for more examples, there is one lecture where I do a lot of examples like this and more than one. I can try to find it for you and point it out over Moodle. Okay. As far as the Mathematica that you did, yeah, save it as a PDF, and it's one of the things you can upload to the link, unless you're somebody that didn't have Mathematica, if your computer crashed. Send me a note if that was the case for you. You can also do a PDF for your notes as well. Okay, as maybe 2 separate PDFs, or merge them if you want. All right, have a good day.